So let's talk about collisions, but with a little bit more mathematics. So we're going to study momentum and impulse, and I'm going to show you something that's amazing. Um, and the idea is because of Newton's third law, which is, like sometimes people say, for every action there is an equal but opposite reaction, and they're talking about forces. This is the third law of motion due to Newton. But this third law is going to imply, and what it implies is this thing called the law for the conservation of momentum. It's really similar in some spirit as to the conservation of energy, but there are some very big major differences between the conservation of momentum and the conservation of energy. Namely, secretly, momentum is a vector, impulse is a vector, energy is a scalar. Energy, the conservation of energy is the conservation of a scalar quantity. There's more differences than just that, but that's a pretty big difference. So this is something that's going to show up. Also, that's going to show up is something that I call a force profile. And it's a force profile in time. And I'll just point out right now, these are qualitative guesses. What a real force profile is between two objects that have a collision, it's really up to the objects, whether or not they're both squishy or both very rigid, or is one squishy and the other rigid. Do they have any stickiness between them, of any sort, like a weird magnetism, or just one's covered in tape residue or something like that. But force profiles really are very specific to what's colliding with what, and also how fast, and what shape, lots of things. But I'm just going to make up a qualitative thing so that we can understand how all of this works together. So here we go. So here's a collision. So A is coming in pretty fast, and it's about to hit an object called B. So A has, let's say it's got a velocity like this. You notice that I am talking in terms of vectors, and if I knew the mass of A and I knew the velocity of A, I could calculate the momentum of A right now. Object B, though, I'm going to just figure out a situation where B is not moving before the collision, and A is coming in and is going to hit B directly, or square, or whatever you want to say. So a little bit later in time, object B actually is still at rest, and object A is just about to start the collision. So here the collision just starts, and so we'll call this T sub s, right? So T for starting. This moment in time was before T starting. So this next step is kind of interesting, because a little bit of time later, actually, let me also still point out that the velocity of A hasn't changed yet, so same size motion. But a little bit later in time, because A has been able to push on B, because A can push on B, B accelerates, and so B into the next time step is going to gain some ground towards the right. So here is B, but the thing about this actually is B has been squished a little bit because A is pressing on that side of B. A is also squished a little bit. So This is kind of tough, but I'm going to say that B has built up a little bit of motion, and A, because B pushed back on A, right, B is going to slow A down. And so the velocity of A is not as big as it was here, but it's still bigger than the velocity of B. That is, A is still pressing up into B. That is, A is still moving faster than B is. Okay, so I'll continue the collision though, and so B has been able to actually pick up a lot of space. Here is B, but A has crushed up on B quite a bit, and now what's going on is the velocity of A has gotten a little bit smaller and the velocity of B has gotten a little bit bigger, but now what's going on is they have a common velocity. This is the moment in time that they have a common velocity. And I'm going to call this moment in time something special. It's going to be T sub m, like this. So this is before the start of a collision. This is right when the collision starts. So let me take that symbol away. You know that S stands for start. And this, T sub m, is at the moment in time that they just reached a common velocity. And now I'm going to draw a force profile. In particular, I'm drawing the force on B by A. You know that we're talking about vectors, so this is a force towards the right on B by A, but I'm not going to draw the little vector arrow because I'm really just thinking in one dimension right now. So this is the force on B by A. And what I'm doing is I'm drawing the profile in time. So I'm going to draw in time. So here is for times smaller than T sub s, the force is actually 0. So the force on B by A before they are in contact, there is no force on B by A, so the value is 0. But at T sub s, this is when the value of the force starts to grow, right? They need to crush into each other and become more and more deformed to have a larger interaction force between them. And so the force climbs dramatically during the time from Ts up to Tm. And I'm going to say that Tm is this moment in time where there is a crescendo or maximum force. Okay, so if the collision is so-called perfectly inelastic, then what happens is as soon as the two objects reach a common velocity, if perfectly inelastic, we could say that this is when the force on B by A shuts off. That is, they stick to each other, and A no longer pushes on B. So I'm going to, in this force profile, I'm just going to turn it off. It goes all the way down to 0, and 0 afterwards. And the idea is, this is kind of what perfectly inelastic is qualitatively. These are qualitative guesses about what a perfectly inelastic collision could be like. The force suddenly shuts off and is simply 0, and A no longer pushes on B, so they don't separate afterwards, right? They're all up in each other's space, they're moving with the same velocity, and if they don't push on each other anymore, then they don't separate again. This is the idea behind what's called a perfectly inelastic collision. You can see that I had a whole bunch of motion here and an object at rest. And now I have this combined object moving slower, right? This arrow is smaller than that incoming arrow. And this is just what it's going to look like for all future times, because there is no more force that's going to cause either one of them to change motion and separate. Okay,